Hi, I'm Mike Poland, a geophysicist with the U.S. Geological Survey at the Cascades Volcano Observatory. This is the first of 2 lessons about Mount St. Helens, and this module will focus on the 1980 eruption, including its buildup and aftermath. The sequence provides a spectacular example of how different types of studies can help to forecast eruptions, as well as the many impacts of a volcanic eruption. Mount St. Helens is located in the southwest part of Washington State in the USA. It is a typical stratovolcano composed of both lava and ash, and before 1980 had a summit elevation of about 3,000 meters above sea level. Prior to 1980, it last erupted in 1857, so there was little knowledge of its activity and potential for future eruptions. That all changed in the 1970s, when the U.S. Geological Survey began studying the Cascade Mountain Range in detail. Based on the ages and numbers of deposits of ash and lava and mud, geologists quickly realized that Mount St. Helens was the most active volcano in the range. In fact, in 1975, they published a scientific paper stating that Mount St. Helens might erupt within decades and that several kinds of hazards would result. It was a very accurate forecast that was based simply on the geologic history of the volcano. In mid-March 1980, earthquakes began occurring beneath the volcano. At first, there was some question as to whether the earthquakes were related to the volcano or caused by tectonic faults. The quakes were volcano-tectonic events, and they increased in number over time, so it was clearly not an aftershock sequence of some kind, when the number of events decays over time. The start of steam explosions in late March removed any doubt the volcano was waking up. Volcano-tectonic earthquakes eventually became so numerous that they saturated the local records, and the quakes were recorded very clearly at stations that were tens of kilometers distant from the volcano. Many of these events were strong enough to be felt in the magnitude 3 to 4 range. Scientists rushed to Mount St. Helens to install new instruments, collect gas samples, and measure how the volcano was changing shape. By April, it was clear that the volcano was deforming. Volcanologists used electronic distance measurement techniques to measure the shape of the mountain, and it quickly became obvious that a bulge was growing on the north flank of the mountain, moving outward by an astonishing rate of 2 meters per day. This was evidence that magma had risen into the mountain itself and was pushing the flank outward. By May 17th, the bulge had grown outward by over 130 meters. But there was no other evidence of deformation anywhere else on the volcano, meaning that magma was able to move into the volcano itself without causing obvious broad uplift. Gas samples were collected from the steaming vents that had formed near the volcano's summit due to small explosions, and also via other airborne and ground-based measurements. Sulfur gases were detected in small quantities, suggesting that the magma in the mountain was trapped beneath some sort of impermeable cap. As all of that precursory earthquakes and deformation culminated on the morning of May 18, 1980, when the oversteep and north flank failed in what is still the largest landslide ever witnessed. This series of animated photographs and the schematic cross-section show how the flank slid away, exposing the magma that had intruded into the mountain. This was like uncorking a champagne bottle. The gases dissolved in the magma exploded outward, creating a lateral blast that moved over the landscape at nearly 500 kilometers per hour, devastating an area of 600 square kilometers. There were no immediate precursors that indicated that the eruption was on the verge of happening, and a magnitude 5.1 earthquake that occurred at the same time was probably the seismic signature of the landslide itself. As a result of the landslide and lateral blast, 57 people were killed, including the U.S. Geological Survey scientist David Johnston, who was monitoring the volcano from an observation post 8 kilometers north of the summit. This was the first well-documented volcanic landslide and lateral blast, and resulted in a new appreciation of that hazard. In fact, the deposits left by the Mount St. Helens eruption in 1980 led to the recognition that volcanic landslides had occurred at other volcanoes around the world, just one of the many lessons the 1980 eruption taught volcanologists. After the catastrophic landslide, magma ascended several kilometers from the chamber beneath the mountain, reaching the surface and resulting in a strong eruption plume of dacitic ash that went over 20 kilometers high. At the same time, the landslide debris released a slurry of mud from the ice and water it contained, creating a lahar that devastated the river valleys around the mountain and deposited enough mud in the Columbia River over 100 kilometers downstream that shipping traffic was stopped for several days until dredging reopened the channel. Ash turned day into night in several parts of eastern Washington, and ash fell visibly as far as 1,500 kilometers away. By the evening of May 18th, the eruption calmed and eventually ended later that day. total volume of the eruption, not counting the landslide, was about 1 cubic kilometer of uncompressed ash and debris. The 1980 eruption removed 400 meters of elevation and 2.7 million cubic meters of the mountain. That's the purple shaded area here. That's the equivalent of almost 200 million dump trucks. What remained was a horseshoe-shaped crater where there had once been a volcano that had been so symmetrical it was called the Mount Fuji of America. Within days after the catastrophic eruption, a lava dome began to grow in the volcano's crater as magma continued to rise from below. The first few small domes were destroyed by explosions, but starting in October 1980, 17 episodic eruptions over the next 6 years eventually built a dome that occupied the center of the crater and was over 300 meters high. The total volume of the dome was about 90 million cubic meters. Intense monitoring of the crater area allowed volcanologists to accurately predict these dome-building eruptions. For example, measurements of deformation on the crater floor revealed acceleration of ground motion as the next eruption approached. Thus, volcanologists were able to make predictions and issue warnings that were surprisingly accurate. The plot here shows the distance across a fault on the crater floor of Mount St. Helens determined by a simple tape measure, as shown in the photograph. Rapid contraction of the fault was found to be an indicator of impending eruption, which allowed volcanologists to predict when an eruption might occur. Seismicity and deformation, and to a certain extent gas emissions, were found to be the most reliable indicators of an imminent eruption, so volcanologists spent a considerable amount of time collecting data from within the crater of the volcano. This remains one of the best examples of eruption prediction in the history of volcanology, and it emphasizes the importance of monitoring parameters like deformation, earthquakes, and gas emissions at active volcanoes. But the predictions were based mostly on pattern recognition, meaning that the trends in earthquake activity and deformation repeated themselves, and so became straightforward to identify. Nevertheless, this is an excellent example of the precision that can be achieved when volcanic activity is well monitored and a good understanding of the data is developed. After 1986, the volcano returned to sleep, with no further dome-building eruptions. A glacier, the blue area shaded shown here, gradually formed in the crater. The May 1980 explosion tapped the deep magma reservoir beneath the volcano, causing earthquake activity to affect both deep and shallow levels. After May 1980, seismicity was mostly within about 2 kilometers of the surface, indicating that the magma that fed the lava dome eruptions was coming from shallower depths, or at least rising without creating deep earthquakes. Low-frequency earthquakes were common during this period, reflecting magma moving beneath the volcano. After the dome-building eruptions ended in 1986, deep seismicity returned, and low-frequency earthquakes became much less common. The deep earthquake activity was interpreted as a sign of pressurization in the volcano's magma system, an indication that the volcano remained active and future eruptions were possible.